What the heck is up, guys? It's Jacob here, and in this video I'm going to be talking about semiconductors. So I originally didn't really intend on making this video. I kind of wanted to stop in the resistance video for my basic physics behind electricity, but I'm starting a series of videos on electronic components, and it dawned on me that a lot of them are actually semiconductors, and I don't have a video explaining kind of semiconductors, and I didn't want to explain semiconductors in general in each one of those videos. So I'm going to refer a lot of those videos back to this video so that you guys can see kind of the basic underlying principles behind semiconductors. So let's get into it. And I also just want to make the disclaimer that this is going to be a very, very, very basic lecture on semiconductors. It's just going to be like 3 slides long, and it's going to be incredibly basic because I'm not even going to lie, semiconductors are an extremely advanced topic, and they can get into like crazy things like quantum tunneling and stuff like that, which goes way over my head extremely fast. So we are just going to examine semiconductors on the level that really, as far as deep as we need to know as electrical engineers to design circuits. We don't really need to go any deeper than this. So we're just going to very basic, just scratch the surface of semiconductors because they are a very quite advanced field, and there's a lot to do with semiconductors in the physics field and stuff like that. So this is just going to be a 3-slide introduction, just scratching the surface of semiconductors. So let's get into it. So I just have this picture here. I just took this picture of different various semiconductor components. We'll look at all those in much greater details in my electronics components videos, but just a few transistors, a couple light emitting diodes, and a couple of diodes there. So we'll look at those later on, but I just wanted to show you guys what these actual semiconductor components look like. Semiconductors are used in absolutely everything. Whatever you're watching this video on right now has probably billions and billions and billions of semiconductors in it. Whatever it is, phone, computer, doesn't matter. So now I want to look at the types of semiconductors. And so to start, I want to look at, well, let's talk about what a semiconductor is first. Let me talk about what a semiconductor is. So if you look on the periodic table, there are like conductors, and a lot of those are kind of in the middle in those transition metals, and towards the left, maybe towards some of those metals. And then towards the right of the table, you have a lot more insulators or gaseous elements or whatever. They're not as good of a conductor. And then kind of in between, staggered down the periodic table, so more towards past the middle, but not all the way to the right, kind of in the middle-ish right. You have these conductors that are called semiconductors, and they don't really conduct as well as an actual conductor, and they don't conduct as poorly, so they're not as good of an insulator as an actual insulator, so they're kind of in between. But they have some really unique properties and characteristics to them which we can control, and they can behave in very unique ways, which we'll look at here. So there are multiple types of semiconductors. I have here an example of silicon. Silicon is probably one of the most abundantly used semiconductors just because it's very abundant in the earth, and it's very cheap, and it's very easy to produce. So that's why it's used. And it has good properties, and it works quite well for most of our cases. But there are other semiconductors besides silicon, and sometimes they do use other semiconductors, you know. So there's germanium and a few others. So it's not always used, but silicon is the most common. So first we see this type called intrinsic, and all that means is this is just a pure silicon or a pure crystal of silicon, so or any other semiconductor. So it's just the pure semiconductor itself. And like I said, these semiconductors don't really conduct electricity really well. And if you don't understand what conductance really is, if you don't understand how electricity actually flows, I'd recommend watching the first video in this series where I actually explain how electricity works and how these electrons actually move between these atoms to create an electric current. It's pretty important that you understand that. But essentially, these semiconductors do not conduct electricity as well as conductors. Their electrons don't want to move as easily. They're not overlapping the conductance band in all cases. They can in some cases, which we'll look at, but not all the time. And so these electrons do not want to really conduct very easily. So they're not really good conductors, but they're not, like I said, as poor as insulators. So the unique thing about semiconductors, though, is they're very unique. We can really modify their behavior and how they conduct. They can actually be in states where they don't conduct very well. They can be in states where they conduct just as well as a metal. And they have some unique properties to them where they don't really behave like metals. So So these semiconductors they have kind of like different regions in which we can say they operate. They don't always behave as like an ohmic material, so they don't always obey Ohm's law. They don't really follow typical temperature patterns that we would notice, so their resistance doesn't vary quite as the same as other materials due to temperature changes. So they behave different under different temperatures and things like that. So semiconductors are kind of weird materials when it comes to electricity. So we have this process called doping, where we add these extra impurities to a semiconductor, and we can see here on the left we have this N-type semiconductor. And so what this means is we add these crystals of or we add these atoms of other elements, and as you can see we have these silicon atoms, and they form a crystal. They have 4 valence electrons, which they use to conduct, or they share with other silicon atoms to form an actual crystal structure. And these phosphorus atoms fit into this crystal structure quite well. They're almost identical to the silicon atom, but they have this extra electron, as we can see here. So this extra electron, but besides that, they fit in quite well with the silicon crystal structure, and they will actually bond with the silicon atoms and have these extra free electrons available, which do provide extra electrons for conducting electricity. So they make it so that these semiconductors are actually conducting materials. So an N-type semiconductor on its own is quite conductive, and it will conduct electricity rather well. Same with a P-type semiconductor. So P-type semiconductor is the same idea, but we're using boron, and instead of having an extra electron, we can see here it has these holes over here, or a lack of an electron. So we can think of these holes actually as positive charges. Even though they're not positive charges, we can think of them and treat them like a positive charge because they are a lack of an electron, and an electron is a negative charge. So we would normally expect in the typical silicon crystal structure an electron to be there, but because that electron is gone, we can treat it like a positive charge, even though it's not really a positive charge. That's how we treat it in semiconductors, and this is called a P-type semiconductor for positive. So N-type is negative because they have these extra electrons or negative charge carriers, and P-type stands for positive because they have these holes, or positive charge carriers is what we think of them as. Even though these holes are not actually charge carriers, and they aren't actually what are actually carrying the charge, it's really just more electrons moving, and as they move they create other holes, but we can really think of it as these holes as being positive charge carriers, and from now on that's how we'll think of it. But one thing I really want you guys to understand that's extremely important before we move on, and it's critical to understanding how these semiconductors work, is that each of these crystal structures are overall neutral, and that's very important to understand. These individual silicon atoms are neutral, these phosphorus atoms are neutral, so they have an equal amount of protons and electrons on each atom, and overall this whole structure is neutral because each atom is neutral. None of them are ions, none of them are actually charged, they're all neutral. So this structure as a whole is neutral. So it's not negatively charged, and this whole structure here is neutral. These boron atoms, even though yes they are missing this electron, really they also have one less proton inside the nucleus as well. So they are overall neutral. All right guys, and before we go on to the next slide, I want to just say one more time that this N-type and this P-type by themselves are rather good conductors. We have these electrons available to conduct electricity, and we have these holes available as positive charge carriers to conduct electricity. So they on their own are very good conductors. So on their own, these 3 types of semiconductors really are not of much use to us. We can't do really much. They don't really do anything for us. They're not that great on their own. But as you'll see in the next slide, we can create what is called a p-n junction, and these semiconductors become quite useful. All right guys, so here is the p-n junction, and I just want to show you guys real quick here. If we go back to this last slide, whoa, that's crazy. I want to show you guys real quick that in this you see that there are a lot of like silicon atoms, and there are these extra phosphorus atoms kind of just in there sporadically, right? And that's, I show it like that because that's how it really is. Really, we're dealing with a silicon crystal structure, this intrinsic semiconductor, and we are adding in these impurities or dopants to change the properties of that semiconductor. So it's not all phosphorus and not all boron like we see in this slide here. It's not like we have a bunch of phosphorus atoms and a bunch of boron atoms. They are actually mixed together. Oh dear, they are mixed together in this fashion. So, but I changed it to look like this to kind of exaggerate and to show what's really happening in great detail, and to kind of just to exaggerate the PN junction here. So let's go ahead and look at this. So recall in the last slide, I really stressed that overall this side here is positive, or is neutral. Sorry, it's neutral. And this side as well is neutral. So these junctions by themselves are neutral. They're not charged, okay? So when we bring these two types of semiconductors close to each other, here's what happens. We have these boron atoms mixed, again, they're mixed with silicon atoms, and they have these holes here, right? So again, we can think of these, we can treat these things like positive charge carriers. And we have these electrons, or these extra electrons from these phosphorus atoms, and these are negative charge carriers. And these negative charge carriers are going to be attracted to these holes over here, and they're going to want to move. Or we can think of it as these holes are attracted to these negative charge carriers over here, and they're going to kind of like swap places. And that's what's going to happen. And so this is going to happen in this, where these two junctions meet, and we call this the actual the depletion region down here. And what's really important to understand, here's what I want you guys to understand, is because before this whole side was neutral, right? And this was neutral, but now we have charges swapping and moving places. Now there are negative charges going from here over to this side, and there are positive charges, not really positive charges, but holes. Again, we are going to just treat them like positive charges for this. They are moving over to this side, right? So now what's happening is these are no longer neutral. What happens is there's an excess of electrons over here on this side, and there's an excess of holes or positive charges on this side. And now what happens is we have this region where there is actually charges, and these are actually ions because they are charged atoms. Their atoms are either missing electrons or have extra electrons, and so this side becomes negatively charged because these electrons moved over to here to fill in these holes, and this side becomes positively charged because these holes moved over here. And this is what we call the depletion region. And so one other thing I just want to kind of tell you guys is this only happens kind of in a close region where these two junctions meet, or this junction, this p-n junction is created. And that's just because, well, if you think about it, what's going to happen is these electrons are going to, again, they're going to be attracted over to these holes, and these holes are going to be attracted over here, and they're going to want to switch places, right? But it comes to a point where it kind of neutrals and evens out, right? Because what's going to happen is this side is going to start to become, it's going to accumulate a negative charge, and this side is going to start to become positively charged, right? So it comes a point where these electrons, when they keep moving over here to fill in these holes, they're going to start being repelled by this because this side is negatively charged, and they will no longer go and start filling in these holes because they just can't make it over there, because even though they're attracted to this positive side here, they're going to be repelled by this negative charge, and it's just the depletion region stops at a certain point. So that's what happens. So the depletion region is just this point in the center where these two types of semiconductors meet. And so one other really important thing that I want to tell you guys about the depletion region, remember before I said these semiconductor materials on their own, the P and the N type, they both conduct electricity. So they're almost like metals, they're almost like conductors. But this depletion region here does not conduct electricity. It does not allow current to flow through it at all. But we'll look at how we can actually apply a voltage or potential difference to actually negate or shrink that depletion region down to a point where it will allow a current to flow through it. So let's look at that. So again, we can treat these as lower resistance conductors, and this depletion region here as a very high, almost infinite resistance insulator. So we have almost, it's kind of like two conductors with an insulator in the middle, right? And so what happens is we have what we call forward and reverse bias. So in the top scenario up here, we have what we call a forward bias. And so here's what I want to show you guys. On the left, we have the p-type material, and when that p-type is more positively charged, when we apply a voltage to this semiconductor, and the p-type is more positively charged, it's at a higher voltage relative to the n-type, which is at a lower or negative voltage, what happens is if you guys go back and watch some of my other videos about how electricity actually works and how current flows, you'll know that electrons flow from negative to positive, or from a lower potential to a higher potential. So we can think of it as what's actually happening is electrons are flowing out of this wire and filling in these extra holes here. So remember before when we had this depletion region, we have these holes here, and that's what's creating the depletion region. Well, when we have a negative electric potential here, there's electrons flowing in from this wire, excess electrons, and those are filling in these holes. And we can also think of the positive side as extra holes coming in. So there's holes coming in from this wire, or electrons leaving, and those holes are filling in for those electrons that were over here. And we're actually shrinking or reducing the size of this depletion region in the middle. And remember before, these semiconductors actually want to conduct electricity, and this depletion region wants to act like a resistor and resist the flow of electricity or electric current, right? So when we actually apply this forward biased voltage, this depletion region shrinks, and it can almost shrink to the point where it's not even, we can act like it's not even there. It is still there, but we can shrink it so small to the point where its resistance is negligible, and the current will be allowed to flow in this forward bias configuration. So current will actually start to flow, and we can get it to where these semiconductors meet, and there's the depletion region is in the middle, and it's almost negligible to the point where this whole thing acts like a conductor, almost like a wire, right? So it conducts electricity quite well. So that is one state. The other state is when it's reverse bias. So when we reverse bias this semiconductor, what happens is that is when the p-type material is more negative, when we apply a more negative potential relative to the n-type. So the n-type is more positive relative to the p-type. When we apply that kind of reverse bias potential, what happens is, you can think of it as just the exact opposite, right? So what happens is electrons are coming in from this wire, and they're just adding and filling in these holes, right? So we can think of it as these holes are being filled in with extra electrons coming in from this wire, right? Because the electrons flow from negative potential or to a higher potential, right? And or we could think of it as holes coming in from this wire, because electrons are leaving and being transported into this side, right? And so what that's going to do is that's going to make this side more positively charged, this side more negatively charged, and the depletion region is actually going to get larger. And this does not allow for the semiconductor to conduct, because again, this part right here is resisting the flow of electricity. It's resisting that current flow. So in this configuration, electricity will not flow. And that is, this basic component that we see here is actually really just a diode, right? And we can see that this is essentially a diode where current will flow in one way, but not in a different way. And again, this depletion region is always resisting the flow of current. It always resists the flow of current, but what's happening here is that the depletion region is getting either considerably smaller or larger. And the depletion region will actually get so large to the point where if you apply any higher voltage or potential, you'll get what's called a breakdown, and a conduction will eventually occur. But we'll talk about that more in other videos. When I talk about the components themselves, we'll actually look at the breakdown voltage of some of these semiconductors, and we'll talk about that. But so that's pretty much what happens in semiconductors. This again is just a very, very basic video. It's as deep of a conceptual understanding as we need to know for all the semiconductors and use in electronics. We don't, unless you're doing like semiconductor research or something crazy like that, we don't really need to understand much more about this, about semiconductors than this to design circuits. But it is really helpful to have this basic knowledge of semiconductors and circuits, and it really helps to, as we're designing some of these semiconductor circuits, to think about what's going to happen. It gives us an intuition as to how these components will behave in a circuit. So also one more thing I just want to say is, even though we've just kind of showed you a diode here, this really is just a diode. There are other types of semiconductors, but really they are all based on this simple p-n junction. So this p-n junction is really a fundamental component of all semiconductors. Really, whether it be a transistor, bipolar junction transistor, or a MOSFET or anything like that, they all are kind of based on this p-n junction, and this is how they work. Again, they are a little bit more advanced, and we'll look at that in those particular videos, but I just want to show you guys kind of how semiconductors in general work. And a bipolar junction transistor or MOSFET is nothing more than this p-n junction arranged in a specific way to where it has a different behavior, but it is nothing more than just a bunch of p-n junctions. And there are other cases where this depletion region is either created or destroyed using not really electric potentials but electric fields, and we'll look at those in those specific videos. But I really just want to kind of give you guys a quick basic video on semiconductors to go along with my electronics components videos, just so you guys have something to refer to if you want to study up a little bit more on semiconductors. But really, this is advanced. This is as advanced as we need to know in semiconductor to do circuit design. So I hope you guys enjoyed this one, and as always, guys, have a good one.